All right, so today I was going to go ahead and do a demonstration bringing together everything we've done over the last couple of weeks, including writing functions, using pointers, pass by reference, and unit testing, which you just got done doing an informal unit testing last week and it turned in on your Hack 5. You'll be exposed to a more formal testing frameworks using CMACA in C and JUnit in Java. Remember that we are online, so if you have any questions, go ahead and post to Piazza or YouTube there. So we're going to do this by going through an exercise here where we design and rigorously test, and that's bolded there, a function to compute the amount of change given, you need to make 77 cents in change. That's going to be three quarters and 2 pennies. 0 dimes, 0 nickels there, right? So we need to output 4 values. Can we write a function to output 4 values? Nope. That's why last week you had to write 3 2-sepia functions. One for the red component, one for the blue component, one for the green component. But this week in your lab, you're going to update that to take 3 variables by reference so that you can use them as buckets so that you can put those values into those buckets. And because those buckets are shared, you are effectively returning multiple values, right? So we're going to go ahead and write this function, and we are also going to rigorously test it. What that means is unit testing. Rigorous testing in this sense means automated unit testing, right? So first of all, what is a unit? A unit in in code is simply some indivisible piece of code, right? It could be a snippet, right? So these 10 lines of code right here. It could be an entire library, right? For example, the math library. That's my unit. I want to test the entire math library. That's a little bit too big. The snippets are a little bit too small. So where's the Goldilocks zone right in the middle of all that? We're all familiar with that term, right? Goldilocks? Goldilocks and the 3 bears. She breaks into the house, tries the first porridge, it was too hot. Tries the second porridge, too cold. The third porridge was just right. So this is too big of a unit. This is too small of a unit. What should be our unit, right? For us, our unit will be a function, right? And this is a perfect unit because it takes inputs and it gives outputs. And you can treat it like what's called a black box. You're not going to look at what's going on inside of it. You're going to simply give it input, feed it input, look at the actual output, and compare that to a known expected output. And that's your test, right? And so usually it's done by a function or a method or something like that. A unit test is a triple, right? The input, the expected output, and the actual output. And a unit test means that you feed the input in it, you take the actual output, and you compare it to the expected output. Your test passes the unit test if the expected output matches the actual output. Right? Now, I put matches in quotations here because if the output is an integer, of course, 5, you can test for exactness there. But if your output is like you had yesterday in your hacks, right, where the Lorentz time dilation, you could be off by several millionths of a billionths of a decimal place. Does that mean that that the code is wrong? No. You just have to build in a little bit of tolerance there. We will accept any answer as long as it is within 1/10,000th of the expected answer. And so for floating point numbers, you sometimes have to build in a tolerance. If it were a string and the expected output is hello, maybe you can build in a tolerance there. You don't care if it's uppercase h, you don't care if it's lowercase h, just that it needs to be hello or something like that. And so you can do your comparison and say that it matches as long as, ignoring case, the two strings are the same thing, right? It all depends on what your tolerance is, what you're trying to test, and how you're trying to test it, right? Generally, the expected output is computed using some other means, right? A calculator, right? Some online resource, etc. Right? It is not a unit test if you write your input. I don't know what the expected output is, so I'll go ahead and run it. Okay, here's the actual output. That must be my expected output. There's my test, right? Is that really a test of your code? You're just pumping the actual output back in as expected output, right? My test works because I assumed it works. That's not a unit test. You need to come up with the actual output generally before you even start to write your code. That's sometimes referred to as TDD, test-driven development, where you write the tests before, sometimes during, after, it doesn't really matter. Some people are really pedantic about it and think that you have to write tests before. Some people say that you should write it in parallel with everything. Some people say that they should be completely different teams. This team over here writes all the unit tests. This team over here writes all the code, and then they come and they have to resolve their differences through the actual testing process. Right? Those are small details, but you can't use the actual output as your expected output because that defeats the whole purpose of testing. Right? You can have what are called false positives. Right? False positives means your test passes, but your code is actually wrong, right? Or you can have false negatives. Right? Your test fails, but your code is actually right. Right? And both of these kind of tell you that there's something wrong with either the test or there's something wrong with the code, right? But they disagree somehow, right? Now, very, very rarely are you going to get I don't even know if there's a term, right? True negatives, right? That would never happen. But anyway, true positives are going to be tests that pass. The test case is correct, and the actual code is correct, and they all agree, right? The other situation, it would be where your test is wrong and your code is wrong, but they happen to be wrong in the exact same way, in which case, it ends up passing or something like that. But I would put that under a false positive. So, testing and having more tests, as many tests as you can, means that the probability of that happening is extremely low, right? Unit testing, in fact, never provides a 100% guarantee that your code is correct. Many tests and good what's called test coverage provide a high assurance that your code is correct. So what I mean by that is, first of all, having more tests will test edge cases, testing errors, error conditions, having as many tests as you can. If I have one test and I call it a day and I'm done, versus if I have a test suite of 100 tests and all 100 of those passes, and over here only that one passes, which one gives you a better assurance of correctness? The one where 100 tests pass, right? Not only that, but you need good code coverage. If your function has a bunch of if, else if conditions, a loop or something like that, you need to make sure that you have a test for every single possible line of code in that function. It covers your code as well as possible. If you have 1,000 tests, but there's this one line of code that never actually is tested or probed, with all of those 1,000 tests, you don't have 100% code coverage. Right? So you do have to write good tests, a lot of tests, rigorous tests. All right. The more tests that you have, the better certainty you have that your code is actually correct. Now, again, is 1,000 tests good? Is one test good enough? Right? It all depends on what you're doing. Right? But in general, more tests is better. Right? Let's see. Testing can be tedious. Right? But it can be made better by using a formal testing framework. And a formal testing framework just basically relieves you of the need of doing a lot of boilerplate stuff. As we're going to see in this demonstration, we're going to use an informal unit testing framework in that we're going to be writing all of our own code just like you did yesterday for your hack. We're going to have a bunch of if-else-if conditions that if the output and the actual output and the expected output, if they match, it passes. We increment a counter, right? And we report that summary down at the bottom. If you use a formal testing framework, like say in C, we're going to be using CMaka. Right? And in Java, we're going to be using JUnit. That relieves you of the need to do all that boilerplate stuff. All you have to do is specify, I want to test that function on that input. This is the expected output. You take care of the rest of the details for me. Right? And that's and all unit testing frameworks are basically going to be the same. They provide a way to test an individual function or a piece of code. They provide a whole bunch of other bells and whistles, like pre-testing commands and post-testing cleanup commands or whatever. But we're not going to get into it that deeply. Instead, what we do is we expose you to it in lab tomorrow, both of those. So we encourage you to both do the C version and the Java version. And then on your hack, we give you starter code to test your stuff along with a bunch of like 68 tests or something like that. And you just have it to add a few more, okay? Using that as a guide for how to use CMaka and JUnit. Maka, by the way, is mocking, right? Mocking means that you are coming up with test inputs, you mock data, not real data, but fake data that you use to test your functions. And so C, of course, for the C programming language, Maka, they just add an A, I guess, right? JUnit is of course for Java unit testing, right? All right, so let's go ahead and come over here and actually do this exercise right here. All right, so I've done everything. I'm going to be doing everything in this demo subfolder here. So let's go ahead and create a new file. I'm just going to put everything into, like you did yesterday, into utils.h and utils.c. So remind me, what goes in utils.h? So what? Prototypes, right? So this is going to be a function that makes change. So what should we call it? Change? Okay. Change what though? Let's give it a better label. Make change? Right. Now, change is both a noun and a verb at the same time. All right. So, but if I call it make change, then it's definitely okay. You're making the noun version of change. And remember that in general, all of your functions should have verb kind of connotations. That it's doing something, so you should name it after a verb. And what do I end my prototype with here? Semicolon. What's my return value going to be? If I want to facilitate error handling. An error code? Initially, we'll go ahead and go with an integer here, and then we'll make that a little bit better later on. And make change. What is this function going to do again? You're going to take an amount, a dollar amount, in the range of 0 through 99 cents, and you're going to output quarters, dimes, nickels, and pennies. So maybe I should outline that in documentation first. What else belongs in your header file? Prototypes, documentation. Right? So this function computes the amount of quarters, nickel, or dimes comes next, nickels, and pennies to give the proper amount of change based on the given amount. All right. So I'm obviously going to need input here, right? Initially, I'll make it into a double amount, right? What about returning quarters? Is this big enough for everybody in the back or not? Okay. Quarters. It should, well, yeah, why should it not be a double, first of all? Quarters. Yeah, you can't have half a quarter. I guess you could chop a quarter in half or something like that. But half a quarter would be a dime, 2 pennies, and then half a penny, and that doesn't make any sense. All right? So quarters will be an integer, the number of quarters that we're going to give back to you. Right? Now, should it be int quarters? Is that passed by reference or is that passed by value? That's passed by value. In other words, I'm giving this function the number of quarters. Does that sound right? Yeah. Why am I calling the function to begin with then? Right? It's going to compute the number of quarters, put it into the bucket that I gave it. Here's a bucket, put 3 quarters into it because I need to make 75 cents and change. So how do I pass by reference, the other type? With asterisk star with a pointer variable. Okay. Int quarters, dimes, int nickels, int pennies. There. Right. We all understand change too, right? I mean, we're not in a cashless society yet. If you got 87 cents and change, that would be 3 quarters, 1 dime, and 2 pennies, right? Okay. All right, what else goes in a header file? We can come back to it. Now, what goes into my source file? The prototypes go into the header file, and I repeat the signature, but then provide a body where we actually do the work. So to do, implement. All right. But what do I do up at the top? I should have an author header, right? So I think the standard that we posted was that at least one of your files needs an author header. And if you're only going to do one, then make sure that you're doing it in the main testing file. But of course, you can do it all over the place here. Right? So I'll wait until I do it with the main testing file with, say, new file utils tester.c. Right? And then I'll put an author header here. Author, Chris, Burke, me, date. What is today? 2021-09-28. And purpose, right? This is a testing suite for the make change function. That's good enough. Okay. Then of course you can cut, paste, modify for each one of your other files if you want to. But in real life, again, if you have an author or copyright header, usually those are auto-generated with a script of some sort because you don't want to repeat that through everywhere and then update it if you update your copyright notice. Okay. All right. So what do I need to include up here, though? I need to include any libraries, including my own library, right? Utils.h. Good. Never include source files. All that does is it copy pastes utils.c into itself over and over and over again in an infinite loop. I don't know what else I'm going to use, so I'll come back up here if I need to. So let's go ahead and implement this. What's the very first thing I should do? How do you do error handling in C? Do you just go ahead and do that potentially dangerous operation because we have an exception that will catch you from falling and put you back up on the cliff? Defensive programming means that we look before we leap. So we're not going to do anything dangerous before we've checked everything out to make sure that it's correct. So the first thing I notice here in the specification was that it's between 0 and 99. Okay? So let's go ahead and check for that. If the amount is less than 0, 0 is fine because that's 0 quarters, 0 dimes, 0 nickels, 0 pennies. If it's less than 0, or because you can't make negative change, that means that you still owe me, or if the amount is greater than 0.99, right, then we'll go ahead and return something. Right? What should we return here, first of all? 1, okay. That's a sensible value. Why should I not return 0?
No error.
By convention, 0 is no error. So I'm going to return 1. Right? But now this has got me rethinking this. What if somebody gave me an amount that was not full pennies? What if they gave me 0.995? Right? Well, that certainly would be in excess of this amount. But what if they gave me 0.501? Right? That's 50 cents and then 1/10 of a penny. Should we allow that? Probably not. So one thing that we could do is we could take the amount that you gave, round it to the nearest whole number, right? By multiplying it by 100 and then taking integer truncation or rounding it or something like that. Except that if you have to make, and then if that doesn't match the original, what we can do is we can reject it. Right? What I can do is I can take that 0.501, round it to the nearest penny, which is 0.50, which is not equal to 0.501, and then I can throw it back at you as an error. Or I could redesign my function so that I don't have to worry about that at all. What if I took my amount in cents instead? Ooh, cents instead. Right? 0 cents, 1 cent, 2 cent, 99 cents. There's no such thing as 100 cents because that's $1. Right? So by redesigning the function, I've taken out an entire classification of errors to begin with. Those are not even possible anymore. And I don't even have to check for them. I don't have to do it. Now it's on whoever's using this function to properly make sure that it rounds to the nearest cent. Go ahead.
Can you make a variable type that's discrete to the nearest hundredth?
An integer is, but it's just scaled up. In fact, in practice, this is how currency is actually done. You don't use doubles or floating point numbers. If you only ever want to the actual cents, your currency would be a whole integer, and then with the idea that when you actually go to print it out, you need to divide by 100, right? Something like that. Right? But then, of course, there are other ways of doing it because financial applications, real financial applications, are under a lot of financial regulation on how stuff actually should work under the hood. And so you'd have to conform to those rules, which would be very arcane and very, very complex, I'm sure. Right? At that point, you say, screw it and use a library. Right? In Java, that's, of course, the currency library. Right? And then it has localization. Yen, for example, is not divisible. But 1 yen is about 1 penny. But it would localize it to whatever currency you're using. Right? And then you can have actual semantic meaning to your currency, that I've got 50 yen instead of just 50 as an integer, versus I've got $50, which is completely different than 50 yen. Right? Okay. Well, if I make that change here, where else do I need to make that change? In the header file, because those don't match anymore. Right? Of the given, and then I also need to update my documentation. If I make a change, I need to update documentation. If it changes the documentation, of course. And I only, DRY, don't repeat yourself principle, I only have documentation in one place, so I only have to change it in one place. Okay? All right, so if it's greater than 99, or if it's less than 0, then I'll return an error code of 1. Oh, sorry, thank you. Cents. Cents and cents. There we go. Okay. Is there any other kind of error that you might want to check for?
Negative?
That's taken care of here. You could separate them out into negative values, return 1. Values exceeding 99, return 2. And then they would know something different, slightly different happened. So I've taken care of cents. Is there anything that could go wrong with quarters? First of all, do we care what's in that bucket already? No, I'm not looking in that bucket. I'm going to simply compute that you need 3/4. I'm going to put that in the bucket. Who cares what's already in that bucket, right? I'm going to replace it. So we don't care what's in the bucket, but we do care about the bucket. What would be an invalid pointer? What would be an invalid bucket?
They had like 4 quarters?
Well, again, we don't care what's inside the bucket, right? Because we're going to change it. If it were a double pointer, unfortunately, there's no way to test for that. It would be the calling function screw up, not us, that would have forced, tried to pass us a double pointer, and there's really no way to protect against that. That's your problem, not mine. I'm the function. I'm the make change function here. Right? But what is a problem? So remember Bret Hart. What did Bret Hart tell you?
Oh, no point.
Yeah, don't dereference a null pointer. Whack you upside the head, right? So in general, that's what you do first. If you have any pointers, you need to make sure that they are not null. If quarters is null, then this is an error, right? Return, and here I'm going to return 1. Actually, I'm going to return 2 here, even though I'm going backwards, right? Is it going to matter at the end of the day? I'm going to come back and change these with proper enumerated types. Yeah.
Just do or statements.
Or, yep, what else could go wrong? Dimes could be null. And which one of those is correct? The color should be telling you.
Okay.
The uppercase is correct, right? Or nickels is null. Now again, if you wanted to be really, really fine-grained about it, you could say check that quarters is null, return 1. Dimes is null, return 2. Nickels is null, return 3. Right? If you really want that fine-grained of control, then you can do that. Right? But we're not going to go that far. There we go. And then I can combine these into an else if. Now, generally, you check for null first, even though cents and quarters and dimes and nickels and pennies, they have no relationship to each other. In this particular instance, it doesn't matter if you superimpose these two checks. Okay? Otherwise, I think that that's pretty good. Right? Before I get ahead of myself, though, what do I return down at the bottom?
0.
0. Why 0? 0 means, by convention, no error. Right? Excellent. If I didn't have that, what would it look like? A couple of problems are going to pop up here. GCC -c utils.c. All right, well, first, let's take care of the first one first. All right, what's it complaining about? Null is undeclared. Where do you think it might be declared? It's the standard library. So now I do need to include stdlib.h. Right? That's where null is defined. GCC, you haven't had to do that in your main because GCC sees this library as so essential that it brings it in automatically for you. But now we don't have a main. And it's not bringing this thing in by default. And so we have to explicitly bring it in. Right? That's why it's best practice to always include it, even if GCC is doing it for you. Okay? That's taken care of. But do you think it's... I don't have a return statement here. But GCC was perfectly fine with that. How can I make it so that GCC is not perfectly fine with that? Wall. And I see warning. No longer errors, it's just a warning. It's lint that you should probably be taking care of. Don't ignore lint, right? Generally, lint is probably bad. Right? It reaches a non-void function, meaning reaching the end of an integer function, but it has not returned anything. Question? No? Okay. All right. So, putting that in there, now everything is okay. It is error-free, it is warning-free, it is lint-free. Doesn't mean that it's correct, obviously, because I haven't done anything yet. I've just done error checking. All right, help me out. How do I make change? How do I determine what the number of quarters should be?
Do your amount and mod.
Okay, cents. If I go mod 25, what does that give me? So 75 mod 25 is going to give me 0 because of the remainder, right? But if I go 75 divided by 25, what do I get? 3, right? What if I do 76 divided by 25? What do I get? I get 3 point something, something, something. Do I really though? Integer, truncation, gets me what I want. Excellent. Now, take a look at that left-hand side. Is that how I assign a value to a pointer? What would that be doing? 75 cents divided by 25 gives me 3. It would make quarters point to the memory location 3, which probably does not belong to me, may not even exist. Let's find out what GCC tells me when I try to do that. I'm trying to assign to a pointer an int value, right? And it's warning me about that. If I shut off the warnings, I think it would still be a warning, yeah, because it's such an important warning that it's on by default, right? So how do I take the thing on the left-hand side, which is a pointer, and turn it into a regular old variable so that I can assign it a value? Asterisk is the opposite way. A regular variable into a pointer. So going from a pointer to a regular variable would be the star operator again. Okay? That tells me how many quarters I have. What about dimes? Dimes is equal to cents divided by 10. Is that going to work?
You have to like,
So let's take 85. What have I done? Divided by 25, that gives me 3 quarters. But have I changed the 85 stored in cents? Nope. If I did 85 divided by 10, it would say you need 8 dimes. Right? Yeah, sure, go ahead. That's one of the plot points of what was it? Office Space, right? Intentionally putting in bugs and redirecting fractions of a cent into your own account, right? Yeah.
So, I think yesterday working out the code, there's a difference between C and Java when you're dividing. So, I think in C, when you divide, what you have doesn't matter, because the first thing that you divide on, the one on the left, is a double, and the one on the right, I was dividing by.
If this were a double, it would still be a double.
Yeah, it would still be a double for C, but I don't think it was.
It really depends. Sometimes the compiler won't let you do that in Java. Sometimes it will. For example, just as I don't have my Eclipse open here because I didn't intend to do it. But if I said A is equal to 3.5, this is a compiler error. I'm 99% sure that it's a compiler error in Java because you are trying to forcibly put a floating point value into an integer, resulting in integer truncation. But something like this, int x is equal to 10 divided by 2, right? This or 9 divided by 2. I think that this will compile and be just fine. I'm not so sure about this one, but if I put them into variables, I think it's going to be okay. It won't be a compiler error anymore if I did a divided by 2. That's just going to be an integer truncation, I believe.
Yeah, I think it's something like that, because it rounded to like a rounded.
Yeah, well, it'll truncate. It'll go down. So if it's 1.99999, it's not going to go up. It's always going to go down.
It truncated for C it did, but for Java it did.
Okay, I'd have to look at the specific, but yes, there is a slight difference between the two
And then
languages.
When I Java for the n number, when I truncated it was like 10,000. I put a point 0 behind it and made it a double.
Made it a double, and now that's basically like explicitly typecasting one of them because 10 is an integer, 10.0 is a double. Yeah.
I was just gonna say, cause, okay, so if you have like 85 cents that we're trying to figure this out, so 85 divided by 25 would give you 3.
3.
Yeah, give you 3, but then you still have 10 cents left over.
Right. So how do I take care of that?
So we have to do a new sentence.
Okay. Let's. Oh, we can reuse the
Reuse
variable.
cents, yes.
Right. Cents is equal to cents minus however many quarters you just did. Quarters times 25. Right. That'll get you the job done. Except that, can we use quarters directly there?
No, you have to use the pointer variable.
The pointer, so dereference it to make it into a regular old variable. And then you might be asking yourself, well, wait a second, that looks kind of like multiplication there, right? How does C know the difference? It's asterisk, asterisk, star, star. How does C know that this is multiplication and that this is a dereferencing operator? No, the white space generally doesn't matter. I could do this. We generally don't. But it knows because this is a unary operator. It sees, I don't see anything on the left-hand side because there's a minus over there, right? So there's no operand over there, but there is an operand on this side. So therefore, this star must be a dereferencing operator. And it has a higher order of precedence than the rest of them, so it executes first. If that's difficult to keep in your mind, fine. Just surround it with a parentheses, right? And now you're explicitly saying dereference quarters and then multiply it by 25, right? And I think that this is a little bit better in practice. This is certainly a little bit better in style, even though it has the same effect, right? Just like when you write something like, say, A plus B times C, and you meant to do B times C first, you don't have to put or surround this with a parenthesis, but that putting parentheses there advertises the intent that you meant to go B times C first, right? Even if it's not necessary. Okay. All right. Once I've gotten the dimes, now what do I need to do? Repeat this for dimes times 10, nickels, pennies, etc. Before we go on, though, is there an easier way to write this? Minus equals? Right, okay. And minus equals. Right. And then I need to update, oh, you know what? Yeah, the cents has been updated. Nickels is equal to cents divided by 5. And cents, actually, I could do copy pasta, right? Dimes, that should be nickels. There we go. And that should be 5, and that should be nickels. Right? And then I move on. Right, but my mind is not in that mode, right? This is a simple enough example, but when you start getting into the habit of copy pasta, copy pasta, copy pasta, copy pasta, change, at some point you're going to go copy pasta, oops, I didn't change everything, and you move on. And so you have a bug like this. How do you know that that's a bug? Through proper testing. I'm going to leave it for now. All right, and then finally, what's left? Pennies is pennies is equal to cents, whatever cents are left over. If it's 87, then you've done 3 quarters, 1 dime, no nickels, and then you have a remainder of 2 left over, right? So you have to put those into pennies. Okay? All right. That looks good. There is a bug. You've already pointed it out. But I want a bug because I want to see that my test case fail. Right? So let's go over to the utils tester here. And let's bring in all the libraries, include stdio.h, include stdlib.h, and also we'll include my library that I just made, utils.h, right? Int main, int argc, argc, char, argv. It's probably okay to do copy pasta on stuff like boilerplate main functions and stuff like that. That's perfectly fine. Yeah.
So do you have to include utils.h for both utils.c and?
Yep, otherwise main would have no idea what you're talking about here.
And utils.c?
Technically, let me show you what happens when you don't. All right, so let's go ahead and do that. Now what happens is you just went back in time 30 years to a time where prototypes didn't exist in the C library. And now a whole bunch of arcane rules start to take over on, eventually you're going to want this make change function. And C is going to start making guesses as to what the inputs are, what the input types are, and what the return type is. Right? You don't want C making guesses as to what your functions do, right? So yes, it'll compile. It'll compile even without warnings. But now you're stuck 30, 40 years in the past, right? And using that technology from back then, right? So that's not something that's not a road you want to go down. Right? All right. Other questions? No? All right, then let's start testing. Right? Let's go ahead and test for that 87 input, right? So my input in a sense input, if you want to, is going to be 87, right? Int quarters, actually no, sorry. Let's just go ahead and, I do want to demonstrate something here. Make change of sense input. Right? All right, so how's this function? First of all, should I ignore the return value? If I'm going to test for error codes, I certainly need to capture that. So int error code, right? And so error code is equal to make change, right? All right, I need to give it quarters, dimes, nickels, and pennies, right? So let's go ahead and create variables for it. Int quarters, nickels, dimes, nickels, and pennies. And then I can pass in Q, D, N, and P. What's wrong with calling a function that way? At line 17, what is Q pointing to right now?
No.
Null?
No, you don't know.
You don't know? Dead beef? Could be 1. It could be anything, right? So this is not how you pass variables. If you wanted to, you could of course say that I'll create a temporary variable here, int t, and then I'll make q point to t, like that. But if you're going to do that, why did you have a pointer to begin with? Just have a regular old variable, q, d, n, and p. Now how do I pass them to my function? How do I take a regular old variable and transform it into a pointer variable? Just the opposite, right? You'll get in the habit of which one is which, right? Certainly the compiler will warn you if you've done the wrong one, right? Just remember, regular variable into a pointer, ampersand. Pointer into a regular variable, asterisk or star. Okay, what are my expectations here when it's 87? In fact, I'm going to put that down here closer to the action. There's 87. What are my expectations? What should Q be?
3.
Okay. And it would be an error if it's not 3. If it's not 3. Or, what's my expectation on the dimes?
1.
If it's not 1. Or, what's my expectation on the nickels?
0.
0. And what's my expectation on pennies?
2.
P is not equal to 2, right? Or, what's my expectation on the error code here, too? 0. So if it's not equal to 0, then any one of those conditions is an error, and I put failed. Excellent. Otherwise, if all of those meets my expectations, then I print, what's the opposite of failed? Passed. You could say succeeded, but then you've got 6 letters in one and then different number of letters in the other, and things don't line up nicely, right? Using these 2 keywords, failed, passed, the tenses are correct. All of them have the same same letters, and so everything will nicely align when we do all this stuff. Cool. Now, you could also make this a little bit more verbose to do, right? Add more verbose testing messages. For example, printf, testing, make change, and then give it the inputs to do, right? ... Right? And that's what we did on your testing yesterday. If you submitted code that failed initially, We told you how it failed. We told you, here are the inputs, here's the expected output, here's what you gave us. That way we communicated to you exactly what we were looking for so that you could go back to the drawing board and say, okay, I'll use those inputs. Yep, I got the bad output there. How do I make it into the good input, right? Yeah. 18. Thank you. There we go. All right. But I'll put in a to-do. I'm not going to do that here because formatting all that stuff, it's just extra busy work. All right. But once you do it one time, then you can start to copy paste, copy paste, copy paste, and then go down that road of maybe I shouldn't be doing that, right? When you screw something up. But for this demonstration, that's what I'm going to do. Right? And you also see why copy paste, copy paste, copy paste. That's a huge red flag. Why are you copy pasting all of this boilerplate code that checks for conditions and prints an error message? And also, by the way, we should be counting the number of tests that pass and the number that failed. Num failed, failed, plus plus. Num passed. Why do we want to do that? Keep track of it and report a summary at the end, right? If you see 100%, are you going to go back and look at, oh wow, 99, that one passed, that one passed, that one passed? You're just going to look at the ones that failed and focus on those, right? And you only get that if you've got a nice little summary down at the bottom. Right? So those also need to be accounted for. Int num passed, int num failed. Be careful. As of line 19, how many have we passed? How many have we failed? I would agree in concept, 0 and 0. What values do these have though?
No.
They're not pointers, so they can't be null. It'd be nice actually if they were null because that would have a value of 0 maybe.
Junk values.
They're junk values. There are no default values. So if you need to initialize them, just like a sum, if you start out with junk values and then you add something, add something, add something, junk plus anything is still junk. So I need to add to 0, add 1, add 1, add 1. Right?
Isn't it a good thing just to make all those equal to 0?
Yeah, it's a good practice too if you want to, like error code 0. These don't matter so much. Sense input, I'm going to be making sure that I reset that each and every single time. So again, not that big of a deal here. Right? Again, you're going to be throwing away all this boilerplate code anyway and use a proper unit testing framework like CMACA or JUnit. And when you look at your, we highly encourage you to take a look at the code in detail tomorrow because you'll see just this big giant block of inputs and outputs, right? The CMYK or RGB values. So RGB, mode, and then RGB. Inputs, expected outputs. You don't even write any of this stuff. You just let CMACA take care of all that stuff for you. All right. What's for my expectations here? 87 is the same thing. Should I repeat a test case? Nope. But if you ever want to repeat a test case, usually a unit testing framework will allow you to annotate it and say, I want this, here's my test. I want you to repeat it 10 times. Right? There are various reasons that you would want to do that. For example, if you are mocking data and you're coming up with random numbers each for your inputs, right? There are situations in which you would want to do this, but you want it to repeat 10 times, right? Okay. For example, a sorting algorithm. Generate a random array, test my sorting algorithm, and the way that I say that it passed is by going through it once and saying, this one is less than this one. Great. Next one. This one is less than this one. Next, less than, and it only passes if they're in order. Checking with whether or not something is in order is your matches criteria, right? But you don't want to just test it for one array. You say, generate 1,000 different arrays and apply this test 1,000 times. And if I've got 1,000 passes, then it's probably good. Right? But let's go ahead and come up with another number here. What else should I test? A what? 99? Okay. What's my expectation there? By the way, I haven't even run it yet, so let's have at least 2 tests. Right? 3/4, okay. How many dimes? 2 dimes. It's 95 cents. So no nickels again, and 4 pennies. Okay. And let's report a, for this one, I'm just going to go back to the main section's version of this and steal their code. There we go. I didn't want to have to write that. All right, now let's actually go ahead and run this and see if our 2 tests at least so far work. How do I bring everything together again? Right, there's no runnable file here yet, right? I just created this object file. Right. Utils.o, right? That's essentially like linking in the math library, and then utils tester.c. And I don't think I used the math library, but if you did, -lm here. Num wrong. Oh, num wrong. All right, fine. Num passed. Num failed. Num passed. Num passed. Num passed. Num failed. There we go. There we go. All right, let's go ahead and run it. Do you think it's going to pass both of those tests? Hey, all right, 100%. I'm done. No. Do I have good code coverage? Remember, I left intentionally in there a bug involving nickels. But do any of my tests cover the situation in which you might have some nickels?
No.
Nope. So what should I do?
Find the test case that uses nickels.
Make a test case that uses nickels. All right. Give me one. 15? 5 would do it. All right. What's my expectation there? 0, 0, 1, and 0. Right. There. It's wrong. Which test case is wrong, by the way? If you were more verbose in your echoing statements and your printing statements, then you could narrow in and, okay, here are my inputs, what's going on there, and then start tracing through the code and find out, oh, duh, right? It should be 5, right? So let's go ahead and just recompile that and run it again. I fixed it. Gotta recompile everything, right? There we go. Recompile that, run it again, and you can start to see the benefit of having, say, a makefile. Because if you have 10, or imagine that you had 50 different source files. You made a change there, you made a change there, you made a change there. Recompile 50 times. No. Type one command, make, and it will go through and say, okay, this file has changed, this file has changed. Recompile. Oh, this file depends on that file, so I'll have to recompile that as well. And that file depends on that file, so I'll have to recompile that thing. And then finally, it produces your executable for you, right? Using all those rules that you wrote in the makefile. We do provide a makefile for both, for anything that's even moderately complicated, we provide a makefile. We've also provided a makefile for CMACA because you have to link in that library there. Right? Okay. What else should I test? Or 3 is good enough? 3 is the bare minimum for the hack this week, by the way. What else should I test, though?
All the errors.
I'm not even testing the error conditions yet, right? So let's go ahead and test at least one of those errors. Sense input, we'll go ahead and say, give it a 100. Right? Do I have any expectations on the quarters, dimes, nickels, and pennies? Nope. I only have an expectation on the error code. Now, if the error code is not equal to, what was the error code again for out of range? 1, was it? Are you absolutely sure? 1, 2, 3? All right, it's simple enough that you probably remember, and I think it was 1, right? 1. What's a better way of handling that? Name your error codes using a enumerated type. Right? Error code. Right. Okay. what should I start out with? No error. Why no error? Start out with that? Because it starts out at 0. It's an enumeration that starts with 0. And 0 by convention is no error. Otherwise, invalid range or null pointer. Right? And now you can use those human readable words to invalid range, null pointer, right? And no error. Now, this is a small enough example that you might say, well, there's only 3 possibilities, so why go to the effort of creating an enumerated type? And I would agree with you. But if you are creating a more complex system where you've got 50 different types of errors, now it's screaming out to you to come up with some sort of a way to handle your error codes. Okay? All right, so over here, I would expect if the error code is not equal to, I'm testing invalid range, right? If it's not equal to that, if it's equal to like the null pointer error, or if it's equal to no error, then both of those would fail. So I want to make sure that I'm explicitly comparing it to get that. And let's test the other error code as well. Right? So how do I pass in null values? Null, 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 null. Right? Now, only one of them is necessary, but if you want really good code coverage, you would try every single possibility. What happens when all of them are null? What happens when the first one is null? What happens when the first one and the last one is null? What happens when the first one and the third one and the fourth one are null, right? Making sure that all that logic is being tested. And it's really easy to enumerate those. And you've now blown one type of test up into 16 different tests. But if you're using a unit testing framework, it's not so bad. It's just 16 lines of code instead, right? And not even 16 lines of code. It's just 16 lines that you put into an array and then let the unit testing framework take care of it for you. Right? All right, so I'll go ahead and go with null, null, null. And by the way, our unit tests that we usually throw at your stuff on the grader, we do test every single possibility. Right? All right, so I shouldn't be checking for invalid range. I should be checking for null pointer, right? All right, let's test it. Remember, you've got to recompute it, or compile it. Oops, and one thing I didn't do is I didn't change this to an error code. Why? That's not necessary, because enumerated types are integers, so the compiler doesn't care one way or the other. But you can still do it, and it's a little bit better style. Bring everything together and let's run it. Think it's going to pass 100%? Oh, it did. Darn it. I'm saying darn it because, let's see. Oh, yeah, okay. I shouldn't be setting this to 100 and passing in a bunch of nulls, right? What am I trying to, if I do something like this, what am I trying to do? I'm trying to test 2 errors at the same time. It's both out of range and it's a null pointer error, right? You want to test things in isolation. If you want to test one type of error, you test it without the other type of error. If you want to test the other type of error, you test it in isolation of the other error. And so you should be giving this something valid, say 50. Sense input. This will lead to the same result, I believe, yeah. But if I had interposed these, if I had put this up here instead, first, no. What do I want? I want
inside your C file, if you like switch the order.
yeah, if I switch these orders, then, yeah, so I did it correctly over here. I think in my demonstration yesterday, I intentionally did it the other way around so that I would get that error. But I didn't get that error here. All right, fine, whatever. In any case, the takeaway there is make sure that you're testing things in isolation. You can, of course, test combinations. What happens when we have both errors? But that should be yet another test case. Okay? All right. Are we still passing everything? Yep. I'm good with that. So what does an actual unit testing framework look like, say in C? I'm going to go to the labs here. I think I checked this out yesterday. Here we go. So this is a unit testing framework using CMACA, or unit testing for your color utils tomorrow, or Wednesday, I guess. Oh, yeah, that is tomorrow. But you can see that it is way more complex than we just did. But we are leveraging the framework itself. When you actually want to test values, all you have to do is specify your values. I'm testing the maximum function here. So I'm passing in 10, 20, 30. What's my expected value for maximum? 30. Right? Here I'm testing 10, 10, 30. What's my expected value for maximum? 30. We didn't end up testing any negative values, but we should have, right? And you're free to add them if you want to. But otherwise, here's us checking for errors. 355 is out of the range. It should be 0 to 255. And so we're testing what happens when this first one is out of range. What happens when the second one is out of range, third one is out of range, etc. And then we've got grayscale tests here. This is pure RGB. What happens when you pass in a purely red color and use the average method? You should get 85, 85, 85. Right? How did we get this stuff? How did I get 85, 85, 85? Did I run my program and say, oh, okay, output 85. I'll go ahead and cut and paste that 3 times?
So use the calculator.
Use the calculator. Or what I think we actually did was we just found an online tool, and that's perfectly fine too, right? That's not A/B testing, but there is a testing strategy where, say that you have 2 teams. One team comes up with their implementation of the function, another team comes up with their implementation of the function, and then you compete, right? You give them both the same inputs, and if they don't match, team A or team B is wrong. Right? If they both match, but they're both wrong, they just happen to be wrong in the same way, right, in the right way, right? Yeah, go ahead.
Is there ever a case where you don't have a precedent available to you to like test something?
If you don't have, what do you mean?
Like, there's no like,
There's no way to get the expected output?
yeah.
Then I would argue that there's no way for you to implement the function. If you don't know how it works, then you can't possibly write it. So on a whiteboard, if you need to, this is the input, this is the output, and let's codify that in code. Right. Yeah.
Could you show me how you check for no pointer? In the not
I think we did it explicitly up here. Find null. There. There we go. We have 3 valid RGB values, 0, 0, 0. And then we test 2 grayscale by passing in null for the first one, valid G and B, null for the second one, valid R, valid B, and then null for the third one.
How did you do it for the utils.c?
Oh, us?
Yeah,
I passed in null explicitly.
for utils.c with like the error code.
No pointer?
Okay, if like any of them.
Yeah, that's what I did here. Over here, we tested each one in isolation. So we actually had, technically, I would say that these are 3 tests. If you really wanted to do them in isolation, you would need, in CMACA and in JUnit, you would need 3 functions. Test to grayscale null first, test to grayscale null second, test to first blah, 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 third, right? But what this does is it basically puts 3 assertions into one test. If any one of those 3 assertions fails, the entire test fails. Right? And this is how like CMACA, this is how JUnit works. It works on assertions rather than explicitly saying, is this thing equal to this thing? No, fail, or else pass. All you're doing is saying assert that an integer is not equal. So whatever this returns, assert that it's not equal to 0. Right? And If that assertion is false, then the test fails. If the assertion is true, then it goes on and tests the second one. They all have to be, all three of the assertions have to be true. That keyword assert is used in pretty much every testing framework. It's not a keyword, but it's an action. Assert that this thing is true. Assert not equals. Assert true. Assert true. We don't do it in this one because they're all integers, but they in your hack this week, there's another assertion that says that assert that they're close, and then I give you the delta, and it takes care of it for you. Okay? All right, when we come back on Thursday, we'll start on the next topic, which is arrays. Right? Or in Java, Java has arrays, but you shouldn't use them. You should use the formal collections library instead. Right? And I'll show you all of that starting on Thursday.